Welcome to the last day of the course. Today we are going to discuss about complex system science. Now we can use it to model some problems that we might face in 5G and in general in future networks. Okay, so I'll have a first slot where I discuss what complex system science is about, and I show you some of the work we have been doing on this. Actually, I'm not going to show this work here, but we have some work going on with IIT KGP and especially with Aritra sitting at the back. So if you want to ask also something about the work Aritra is doing, you feel free to interact with him. So before we start the last two sessions, any question, comment? Must be tired by now. Yes.
What is the difference between access point and the base station?
Yeah.
How they differ?
Yeah, I don't think there is really much of a difference. I mean, it's terminology. So I think they are both like points of access to the network. So they are like essentially the endpoint of the infrastructure, and then from there on you have the radio link. And traditionally, base station has been used as a term in the cellular network community, and access point in the Wi-Fi community, but it's not really that different. I mean, of course the technology changed, but I don't think there is much of a difference. To me, at least, they seem very similar as concepts in general. Yeah. Any other question? Okay, so what is complex system science? So traditionally, actually, science has been exploring quite a bit the microcosm. So you can think of quantum mechanics and the likes, and macrocosm, and you might think of relativity, right? Black hole theory, these kind of things. So essentially, if you want the elementary particle physics and these kind of things are about the micro scale, so very small scales, and astronomy, cosmology, this kind of sciences are more about the macro scale, right? Very, very large scale. Now, surprisingly, if you look at the history of science, there has not been probably a lot of work done at the scale we are more interested in. So like the average scale, of course you have a lot of works, but let's say the real big theories that came up in science in the last century are more concerned with extreme scales, not with the scale where we live in. Okay, so there has been some attempts from a science called complex system science to deal with this kind of moderate scale. So I'm going back to that. Other phenomena like chaos, non-linear relation between input and output, they have been kind of neglected by fields like control theory, for example, okay, or science and engineering in general. Other things engineering has traditionally done is to adopt what is called the reductionist approach, which is essentially decomposing a system up to the tiniest parts, and then that way you can understand the system. For example, you can think of a clock, and the clock is just an ensemble of parts, cogs, right, that somehow interact together. So it's very possible to decompose the clock, study it, and then that way you understand fully the clock, right? That's why you have like people repairing clocks, right? Or anything like a plane, even a solar system to a large extent. You can think of it this way. So once you understand the parts of the system, you are kind of understanding the whole system. So it's very much of a top-down approach, engineering to date. So you have a design, phase, and that you can basically plan everything according to this top-down approach. Okay, that's what we do normally. That's what science has been doing most of the times. Now, is that the whole story? No, because there are some phenomena which I try to depict in. They try to depict in this figure, which actually escape a bit the traditional reductionist top-down approach. So, for example, things like self-organization or emergence, like you have entities that act based on local information exchange, very simple rules of operation, and yet you have very complicated global patterns. You can think of a flock of birds, where actually the individual birds, they pretty much are very simple animals, so they follow very simple rules, and yet you get very complicated and sometimes fascinating pattern. If you see a flock of birds, how they evolve in the sky, it's as if they were all kind of, they're actually as one thing, but there is nobody in charge. Okay, so it's not really a top-down approach to things, and there are many other examples. Other things that have been a bit shuffling the deck of cards in science are chaotic phenomena. So basically these are a chaotic system essentially is a system, I mean simplifying a bit, that obeys a property called sensitive dependence on initial conditions, or in common parlance it's called butterfly effect. So essentially what it tells you is that unless you are infinitely precise about knowing the initial condition of a system, if the system is chaotic, very soon you will not be able to predict the system evolution in time. Very soon, I mean really soon. Okay, so this is not true if the system is non-chaotic. Essentially, even if you have some mistake in the initial condition knowledge, you can still predict with some margin of error the evolution of the system. But chaotic systems are not like that. You really have no clue, and that has implications also in the design, because if you can predict too far ahead in time, it means you have to be refreshing your knowledge of the system very often, and feedback should happen very often, right? And for example, chaos has been applied in circuit design, chaos theory, traffic. It's more fractals maybe, but you know, to some extent in fractal in traffic modeling, especially for data traffic. Another. So you actually we have been recently writing a paper about the history of chaos and in general nonlinear dynamical systems in wireless, and there has been some work. Okay, so we wrote a magazine. It's currently under review. So hopefully at some point it will be published. So that could be a good reading if you're interested in the topic. So we went through the history, and you know there is some work actually that has been done. Another important concept is the concept of scale in a complex system. So what do I mean by scale? Essentially, think of it, it's probably easier if I explain it with an example. So think of it like the solar system. Okay, the solar system, if you look at it at a large scale, it's essentially not such a complicated system, because you have a big ball, you know, in the middle, sort of. And then you have other smaller balls orbiting around, right? So you have the sun and the planets essentially. So if you look at it at a very large scale, it's hardly a complex system. Okay, whatever the definition of complexity, I'm going back to that, because when you talk about a complex system, you have to tell what you mean by complex also. But if you start to zoom in, and you, for example, you zoom in on the planet Earth, the picture changes, right? And it's difficult to call this system simple. You start to have weather phenomena, right, and all sorts of human activities and so on and so forth. Natural, you know, nature plays a big role. So it's definitely, you know, if you just observe any part of the world for a while, you will see a lot of dynamics, right? Things that are hard to model with an equation. While if you look the solar system at a large scale, you have equations for that, right? For a while, actually, we had them. So the scale is something that plays a big part of the story. You can't really talk about a complex system unless you specify which scale you're talking about. Okay. Yeah, and generally, these are phenomena that are, you talk about a complex system normally when the interaction between the entities is more important than the entities themselves. What do I mean? A good model to study a system is possibly a network model, or if you want to use a more mathematical jargon, a graph, right? So you could depict the entities interacting as nodes in this graph, and then if two entities interact, you might have a link or an edge, right, between the two nodes. So normally, if let's say if you actually have a system which is simple and a system that is complex, and you have the associated graphs, you will see that the structure of the links in the complex system is much less trivial. It's much more intricate, okay? Because in essence, a complex system is also about exchanging information in a non-trivial way. Okay, so you have these local interactions, but yet at some point, if you do the right things locally, you will have emergent phenomena that are very sophisticated. So there is something going on which we don't fully understand yet about how information is actually flowing through the network. So the topology of it doesn't have to be a communication network, it can be any system. The topology of the graph representing a certain system is actually what matters, and not, again, doesn't matter so much the number of nodes, it's more how the links connect the nodes. Okay, that's something that you see normally in complex systems. And definitely the systems are bottom up. You do not have a central entity in charge. So they are normally, they've been, I mean, there is a reason why people like us started to consider them for wireless systems, because the wireless systems are more and more moving far away from something you can optimize centrally, right? Because you have, we saw, I mean, in this course, for example, the emergence of IoT and small cells and integration with Wi-Fi and, you know, possibly in the future even worse, because you might start to have a lot of mobility involved with drones. So you can't really, you don't have the capability to optimize this as we normally did in the past. So in the past, a very common approach for a communication engineer was to write an optimization problem. I want to maximize the throughput over that network, given some constraints on power and minimum throughput maybe, and then I will act based on us allocating channels and powers. I'm pretty sure all of you worked with similar problems or read some works like that, right? So that was the thing. But you see, if you start to have, let's say, I'm making it extreme, 1 million of nodes in a certain area, okay? Possibly you have something like a square kilometer area, and each square meter you have a sensor. So you're talking about 1 million nodes now, right? 0.1 crore or 10 lakhs, yes, that's what it is, I think. So a lot of sensors, and especially if you talk about this low latency, you know, maybe it doesn't have to become like 1 millisecond, but we are talking milliseconds, okay? We are not saying, you definitely have applications that imply a lot of sensors, a lot of transmitters, and cannot wait a few minutes, right, before you do the optimization. So you can't possibly do this. There is another problem, it's not just the time, it's also the signaling overhead. How much information do you have to collect before you take a decision? So you see, it's not that you want to decide once and for all, you have to keep deciding. So it's hard, very hard to have this solved optimally. We have, I mean, it's not something we have published and we have a patent pending, but we are doing some work where we have concrete evidence, okay? We are even going toward possibly experimenting this in, you know, with a test bed, and it turns out that some problems of relevance to 5G are definitely NP hard, and you have no hope whatsoever to solve them. Well, you can, but you have to wait a long time, and it would be useless in the end. Okay, so if you solve the problem by the time you don't need it anymore, it's outdated anyway. So these approaches that are based on bottom-up, local decision making, and so on are actually a good idea. It doesn't have to be only what I'm going to talk about in these lectures. There has been a good, very big amount of work on game theory. Game theory is partly overlapping with this field, and in fact, it's not surprising that they partly overlap because the philosophy is very similar. You have independent players that take decisions, but again, you don't have a central guy. You might have some coordination, yes, but you don't have a central guy deciding for all the players. Okay, that's normally where you draw the line between distributed techniques like complex system science or game theory and optimization. So now it sounds a bit vague probably at the moment, but it has been already applied, okay, and with success. So I'm going to talk about the applications to some of the applications to communication systems, but it has been there, I mean, for a while. For example, it's a popular approach in some problems in physics, biology, computer science. Definitely among the early adopters of this philosophy were physics and computer science. Okay, so the works I found most interesting in terms of engineering, let's say, approaches, they probably come from computer science, actually, not from engineering. And if you talk about information theory developments, in my opinion, the most innovative works, they normally come from physicists, not from communication theorists. So that's my personal opinion, of course. You know, it might be debatable, but I do see more novelty in terms of information theory in physics at the moment. I don't have too much time. I have a full course on it used to be a full course. Now it's probably more of a alpha course, but I do have a lot of material I'm teaching on complex systems. So if you want, I can share it again, and you know, books, and so we have actually a good bit. We have a website where we actually do. Show it to you. This kind of, you know, where we put the things we are doing. So this is a subset of the activities we have in Trinity. Okay, but that's where we talk about the complex systems. So I have to put www, I think. So basically, my center is Connect, I told you. So there is a website, it's called www.trickle, trickle like, you know, the thread of water, right? .connectcenter.ie, where we actually, it's a simple website again, and we are not such good web developers, but we have, I think there is the basic information. So we have essentially mainly 4 areas where we work. So how information theory and complexity theory kind of meet. For example, the work we did with Erythra, I think can fall under this category. I don't think we actually updated even the publication list with your paper. I should remind Mary. Did you know we had this website? Yes. So okay, another is computational modeling. It's essentially these models that mimic nature in the bottom-up approach. So for example, doing what birds or bees or ants do, it's another way to study these complex systems. Network science is essentially application of graph theory to complex systems, and yeah, we have some work in that too. For example, a very big application of this is recommender systems. I told you a few days ago how Amazon suggests, you know, so basically they guess there should be a new link in a network between users and content. So if you like content A, B, and C, they might have very good reason that you like also content D, if according to them they are in the same category. So they suggest you might be interested also in content D, and what they're doing, they have a graph, and they force you kind of to create a new link. Yes, so That's an application actually of network science. I'm going to tell a bit more about this later on. And then you have nonlinear dynamical systems, so where the input-output relation is not linear, is not what control theory normally does. So this is a field that is essentially in the overlap between control theory and communication theory, if you want, for what we are concerned. But definitely control theory plays a role. It studies the evolution in time of systems and how you can actually use feedback to control a system better. Control, I mean, could also be mechanical movement, like actuation, not just, you know, nowadays with IoT, we move away from wireless sensor networks in this sense. It's not just sensing, you can also control things, right? Actuating. You might change the temperature in the thermostat, right? That's something that is changing. You know, you have all of this work on industrial automation, using communication systems to improve industry operation. They call it Industry 4.0. It's another standard altogether. They talk with 5G, but it's something else. So that's another big thing that is coming up. Industry 4.0. They have their own standard conferences, right? And we do interact with them, but they are another community. These are the guys operating plants, operating factories. Okay. So all of this, and then you know you can check again what we do and so on. But just to give an idea of, these are traditionally, my understanding, the four main areas of complex system study, and we do. You have actually people that are doing these things for other systems. We are focusing, of course, on communication systems. So it has been applied in many other fields like transportation, market, you know, studies, and essentially you have different scales playing a role in these systems, from small ones to larger ones. You normally have systems that are not fully predictable. So there is some element of stochasticity, okay? They're not, at least it's not so straightforward to write an equation to see what's going on. Okay, these are not the systems we're talking about. Okay, so in some, there is a nice book, it's called Introduction to Complex Systems, probably by Melanie Mitchell. See if I can find it. That's the first book I read on the topic. It's nice actually. It's very easy to read. Okay, it's not a very technical book, but it's a very good introduction. Let's see if I can find it. She's from Portland University, as far as I remember. Yes, that's the book I'm talking about. So it's called Complexity: A Guided Tour. Very nice intro, actually. Very easy to read. So you might want to read that if you are interested in this area. She's also affiliated with it's called Santa Fe Institute for Complex Systems in US. So this kind of is the world leading center for complex systems, and they have some permanent faculties, not too many as far as I know, but they do have guest faculties from around the world, and they are the world leaders in complex system studies. Okay, in general complex systems. I don't know, probably a few of you saw the movie Jurassic Park. Do you remember the crazy mathematician, what he was doing? He was a guy, right? It was Jeff Goldblum, the actor. He was the scientist. He was kind of brought there, as far as I remember, to observe, right? So they kind of wanted the stamp of science. Then it ended up very badly. I'm not spoiling anything, I think. We know that the movie has some twists and turns, but they basically want an independent expert to validate that everything is all right and science is applied correctly, which doesn't turn to be the case, right, in the end. But that's the scientist they bring in on this island. And you remember what he was studying? Anybody? He was actually an expert of chaos theory, and he was affiliated to the Santa Fe Institute in the movie. Okay, it's not true, but yeah. So we go back, right? What? Probably 25 years or something like that with that movie. But that was the time where, you know, these topics were really even mainstream, right? If it appears on a blockbuster movie, then that tells something, right? So emergence is very much at the heart, okay, of complex systems. It's something we don't fully understand yet. We just observe it. It's essentially how a macroscopic behavior arises from a microscopic behavior. So you have entities that emerge, or properties, say, that emerge out of more fundamental properties or entities, but they are not made of the same stuff, so to speak. They do emerge, but they are something else. So you have the simple ant or the simple bee communicating with the neighbors in a very simple way, and then you have a very complex structure, a fully functional colony, right? And again, yes, there is a bit of coordination by the queen bee or queen ant, but it's not like that there is somebody in charge, really, right? And flocks of birds and many other examples, or school of fish, a school of fish, right? These kind of things are, you might find many videos online showing this kind of, you know, collective behaviors. So why am I saying philosophy? For example, the book I just told you about, this complexity guided tour, at least in my university, is classified under philosophy. So this is not pure engineering or pure science anymore. You do have some concepts about how you study things that are more of a philosophical nature. It's like philosophy of science, if you want. In fact, there is a huge fight, a huge clash going on behind the curtains between the people that think this is a good field of study and people that think this is rubbish, honestly, okay? So there is a tension in the scientific community because the successes of the reductionist approach has been immense. All of what we do nowadays in terms of engineering and science is sort of based on this reductionist approach. So it's top down. You can decompose a system and you understand it. That's what you do in labs throughout the world. But there are some systems that objectively escape this. Now, the reductionist and the reductionist people acknowledge that they can't study those, like weather. Weather is not something we can model very easily. And they say it's just because we are ignorant, we don't know enough. And then there is the kind of, you know, emergence people, complex system science people, they say no, it's just that you are using the wrong tools. You need a new set of tools to study this kind of system. And there has been some good success from the complex system science people too, though it's a much younger field, but it's essentially two of the main school of thoughts nowadays in how to do science. So it's way beyond the application to 5G. That's what I'm trying to convey here, okay? So the reductionist people, they say pretty much we have some few fundamental forces in nature, and at the moment, as far as I know, is 4. They leave the door open that there could be more, but not an infinity. There is still few, okay? And so the number n is small. The people that are called, they believe in strong emergence, they think that we are just missing maybe other forces just because we don't look at the right scale. So it could be actually that there are new laws, and you just have to basically study it with the emergence lens and study it at the right level of abstraction. One example that is actually could probably be the tiebreaker is life. We don't know at the moment how life is about. We don't. We observe and we have an idea when it started on Earth. Somehow we have an idea of the conditions, generally speaking, but there is nobody at the moment that can claim they can produce life in a lab, right? And until you do that, this question is not going to be resolved, in my opinion. So it could be that actually we need a new viewpoint if we want to understand these kind of things like biology, okay? So the problems of complex systems are actually what we call problems of organized complexity. What does it mean? It actually means that they are in between problems of two kinds. So on the one end of the scale, you have what we call problems of organized non-complexity, and they're essentially problems with few variables involved, and they are by all definitions simple, and they can normally be expressed by simple mathematical formulas. Examples like when you study the motion of balls on a billiard table, that's something you can study with Newton mechanics, and it's not so difficult to study it that way. But already when you have three bodies interacting, it starts to be very complicated. Okay, so it's normally not so easy to scale this up. Another example in our field is information theory. You have closed form expressions for very simple networks. Links, of course, relay systems with 3 nodes, interference networks with 4 nodes. I'm afraid that's more or less it. And then you have other approximations for larger systems, but you see, these are systems that are normally very simple and very small in the scale. On the other end of the scale, you have disorganized complexity, which is essentially something that is normally studied with the help of statistics. An example is statistical mechanics. They actually study properties of, for example, of gases, like temperature, pressure, and so on, based on statistical interaction, like based on statistical tools. Because you can't model trillions of particles, even simulating it, you couldn't manage that, right? So they do some simple assumptions about how the particles interact, and then you do basically study the macroscopic properties somehow. Complex systems are normally about something in between, what we call organized complexity. So there is a moderate number of variables and interrelationships. There is no number associated to what moderate means. It's something that is not 3, and it's something that is not a trillion probably, okay? So, but again, there is no specific number, and you don't have enough interacting agents to use statistics properly, and they are not simple enough so that you can find an equation normally. Okay, that's what we are talking about. So there has been a recent increase in this kind of problems. Again, for example, in our field, it's because they kind of resemble situations we are dealing with. And this is a definition that is given in this book I mentioned before, and I think it's a good one. So a complex system is a system where there is a large network of components. There is no central control. There are simple rules of operation. This simple rule of operations yet give rise to a complex, so more complicated than the starting point collective behavior. Somehow information is processed in a sophisticated way, and that's what leads to emergence. And they might be able to adapt to the environment, even possibly via learning or by evolution. So there are many things here, okay, in one definition. It's not a very formal definition. I don't think we are at that stage yet. But that's the best definition I found so far. Okay, now going a bit more into something a bit more formal. So we talk about complex system. So first of all, what is a system? A system is a collection of entities that interact. Period. I don't think there is much more to that. So I'm asking a question now. If you have a set of teacups, you have like a row of 5 cups with chai tea inside. Do you think this is a system in the first place? Now, remember what the definition is, right? It's a set of things that interact together. Do this chai cup interact? Let's say the chai is gone. There's not even heat. Empty cups. Do you think they interact? Well, I don't know what is your experience with teacups. They normally sit there, right? They're very, very polite. They don't really take much initiative, right? Unless you have robotic teacups, I don't know. But in general, this is a set. So a set is just a collection of things. That's what it is. If you start to have interactions between the things, then you can talk about a system. Now, that's fine. So when does a system become complex, though? So one way could be to observe, like, if there is input-output relations that are not linear. So you give a certain input x, you observe the output y, and then you give another input x1 and you observe the output y1. So if you plot the inputs on the x-axis, the quantities, and if you plot the quantities for the output on the y-axis, and you have a line, that's normally, that's what we mean by linear system in this context, and that's what control theory is all about. Current control theory, mainstream control theory. If you start to have relations that are not linear, sublinear, or superlinear, that's an indication that the system might be complex. Okay. Other things, you definitely do not have the possibility to kind of control or optimize the system centrally. These are all good, but there is another thing we are missing. It's like we talk about a complex system. So what is complex? What does it mean? So any guess? So when I say something is complex, what would you think I mean? Any guess? We're going to see a few definitions, but
Set of devices connected with each other, or you can talk to each
yeah. So, but complex. How is that complex and not simple? What you know? You have to. If you say something is complex, you also have to give me an example of something simple, right? So, where would you draw the line? What is complex and what is simple?
There's multiple entities correlated with each other in a distinct form.
Yes, but where do you draw the line? Where does it become
Relative term.
correct? So, but you could think of extreme cases. So, can you tell me some example of things that are definitely simple, even in your life experience, and some things that are definitely complex? Okay.
Higher entropy.
Hmm?
Higher entropy.
Higher entropy is a good guess. Okay, entropy essentially has to do with randomness, right? Disorder, and in fact, there are some definitions that are about that. For example, if you Kolmogorov complexity is actually about that. There is an issue though, going back to that, but yeah, that's a possibility. Any other guess?
Students sitting in a class, they are simple, but when they are in a corridor in a random,
Because the interactions are a bit more intricate, right? You start to have more of a mesh network, right? Here it's more like a broadcast, right? I'm talking, you listen, and or maybe there is a bit of interaction, but yes, I think that's a good example. So interactions matter, possibly randomness matters. So in a sense, you go back to the Shannon information concept. Something is surprising, therefore it gives you more information, right? So it could be a way to see it, yes. Other guesses? So, in general, you see, that's where I start, like talking a bit more formally. Complexity and entropy have something to do with each other, but they are two different things, at least in the field of complex systems. So you do have entropy does not capture things like correlation or structure, which essentially have something to do with complexity. You can't neglect that if you want to talk about complexity, right? But there is some relation between the two. And in fact, the relation is very, well, it's kind of acknowledged, okay, and you see, this paper in physics. So the interesting concepts that are more of an information theory nature, they come from physics nowadays, in my opinion. So generally speaking, a system like this, let's say you have a crystal, you have a very regular structure that repeats at every scale. If you take a bit of the system, a tiny bit, or you take the whole system, it's always going to be the same. A checkerboard, right? Like a board where you play chess, it's definitely going to repeat, right? So in this case, if you measure some form of complexity and order, so you have to have, I mean, in this case, you would have very low complexity and very low disorder, or very high order if you want. On the other extreme of the scale, you have structures that are very random, where there is, even if you start to zoom in and out, you have no clue, right? You have a string of symbols which is random. You can take a part of the string, the whole string, you again would not have very much of a clue what's going on. So it's actually, there is no structure at any level whatsoever. That's the problem with saying that the system is, the more the system is random, the more it's complex, because there is no real insight. So you should have some kind of structure that is not trivial. There has to be structure in the first place, so I think randomness is not really what we want. But on the other hand, we also do not want this thing, because this is not giving us any real insight. So this cannot be complex. Okay, this is something that is very dull. So you have to have some kind of non-trivial structure in your system. So when you have systems where you have non-repeating structures at multiple levels, so you keep zooming in or out and you get new insights, this is what normally we call complex. And for these systems, you have a complexity that is fairly high and a randomness or entropy that is moderate. And then you have the random systems where randomness is maximum, but also complexity is 0. So you have this kind of behavior, okay? And we verified this for some communication systems, for example.
It is combining the real structure with the randomness structure.
You kind of have something in between, exactly. So you need to have some structure, but you also need to be a bit surprised. So randomness plays some role. You're right. So we are going back to this relation between randomness and complexity. Now, there are many definitions. Honestly, quite a lot. Okay, we do not have like one definition of complexity. I think we are in the order of 100 now. Aritra, what do you think? Something like that. So you have to pick the one that suits you best. Okay, it's more of a collection of definitions. So you could think of size, though it's not the full story, but it tells something. Okay, if a system has a lot of components, there might be a chance for it to be complex. But you also need the parts to be interrelated in a non-trivial way. Could be ignorance. It could just be, that's for example the critique that the reductionist people normally raise. They say, okay, you call it complex just because you don't understand it. Okay, and it's their viewpoint, fine, okay, and nobody's right or wrong at the moment. So the brain is too complex, and it's just because we don't understand it. Okay. Another way is to describe the system somehow. So after all, science is about telling stories about things that happen, right? So you have to describe things. So possibly you could describe the system in some language. Maybe usually they use Turing machine as a universal, computing machine, and basically the complexity is the minimum possible length of the description. So when you really get it to the shortest possible description for the same for that system, then you call that complexity, and it's called Kolmogorov complexity. The problem with this is that the highest complexity would be for something random in this case. So if you think of it as a string of bits, the most complex case would be the case of a totally random string of bits, because the minimum description length, yeah.
Can you say that complexity is the measurement of uncertainty of interaction
I
among several nodes?
I think it's a way to say it, yes. I think it could be one way to say it, yes. So you see, if you have a string of bits which is very random, like completely random, say, how do you describe that in the most efficient way? Essentially copying and pasting. You can't do anything else. You have no clue about what's going on. You can't infer things. On the other hand, if I give you something like 1, 1, 1, 1, 1, 1, 1, this is very simple, because I can just tell you a program which is very short, print 1 forever. Right? This is very clean. But if I give you something which is changing all the time according to something I don't understand, possibly random, then the complexity is very high, because I have just to copy. Now it could be, again, I'm not understanding, so it could be that eventually the complexity will reduce, but at the moment I see just a random thing, so I'm just going, again, perception might change with knowledge. The digits after the decimal point of the number pi have no structure whatsoever, but we know how to generate pi. It's basically the ratio between the circumference and the diameter of any circle. So you see, so if you give this number to an alien that doesn't know geometry, would probably say, okay, the Kolmogorov complexity of this number is very, very high. But for us, it's something you you are taught in primary school. You see, because so knowledge might play a role. I'm going back to this thing. Variety is normally something associated with complexity. So if a system is pretty much composed by homogeneous things, it's not normally a sign for complexity. And there is a relation with disorder. Normally we say that complexity is kind of a midpoint between fully ordered and a fully disordered situation.
The complexity reduces when the disorder is
It's normally they are no, they're really two different axes. So you kind of have, it's normally showing up at the midpoint, okay? And there is, I think that John is right, there is some relation, but they are also two different things, okay? So, okay, another thing, for example, another approach could be you define complexity as the difficulty in describing something. So you basically have measures like entropy, information, yeah, this minimum description length I told you about, and essentially you are trying to describe the system and you see how difficult it is to describe it. So definitely the human brain is more complex than an apple, probably. I think it's fair to say, right? It could be the difficulty in creating something. So it's not just you're observing, you're trying to make the thing. Okay, so it's associated with the difficulty in constructing or duplicating a system. For example, how much computation would take you to do something? How much time it would take you to do something? How much space it would take you to store the information and to do something? And so on and so forth. There are costs, okay, this kind of thing. So if you go by this definition, possibly you could say, for example, that a human organ is less complex than the brain. Why? Because you have artificial organs now, you have transplants. No way you can do that with brain at the moment. If the brain is damaged, done, right? So that there is something there. Life is more complex than the brain, correct? As far as I know, nobody can create life. As far as I know, you can't bring back people from the dead, right? That's the realm of religion, but science cannot do that, right? So I think it kind of is not a bad definition, okay, because it kind of gives you some idea of complexity, right? The one we have been mostly using is this one, though. So it's the degree of organization. So essentially, it's how difficult it is to describe some organizational structure. It could be a cellular also in the biological sense, I mean, chemical, corporate, and so essentially how even visual is the complexity. So this is something we thought about because a lot of the things we do in communication networks are about taking decisions over some space, and you could even picture things with different colors if you want. So for example, what we did, I'm going to show, you could think of channel allocation in this way. You give it a color. If I use channel 1 is blue, if I use channel 2 is yellow, and so on, and then you see visually what it is. So it gives you some perception, and then there are metrics to compute things more formally, but essentially it's how things are structured over space. So the minute you are visual, or at least it doesn't have even to be visual, but you have some kind of representation of a system over some space, structure is there, right? You start to have graphs, stuff like that, okay? So again, it doesn't have to be a physical space, it might be something you don't see. Maybe it's many dimensions, more than we can visualize, but still there is this concept of a space and the relations over the space. So this is something that we normally do in communication systems. Channel allocation, you know, association of users, power maps. You know, when we represent things like, you know, SINR maps, right? It's kind of a heat map. Again, visually, you start to see structure there. So structure is somehow something we play with, even if we don't acknowledge it. Another thing we are interested in, so there are two subclasses of this degree of organization complexity. Another one is the information shared between the parts of a system as a result of the organizational structure. So what I mean is like how you actually exchange information, so how you signal information, something you could measure, and things like mutual information is pretty much about that. So the way we define the Shannon capacity is to maximize, is the quantity that maximizes the mutual information. So the information shared between a transmitter and the receiver, right? So we, again, without thinking maybe in these terms, we've been doing that for a while. So we are going to focus on these two, okay, for as far as we are concerned. So as an example of this first metric, so the difficulty of describing organizational structure, we are going to use a quantity called excess entropy. I'm going back to that. That will capture the structure resulting from some collection of self-organizing networks that actually play with channel allocation. Okay, some form of cognitive system, if you want. And then, essentially, we want to understand how much structure is present in the spatial abstractions with which we model our networks. Spatial, again, doesn't have to be the space we are used to. It could be multidimensional thing, but in very often we can get away with 2D. What we do, you see all the things about stochastic geometry and so on, topology, then cells, they are always in 2D. Now you might start to have 3D. There are people working in 3D models, 3D beamforming, 3D channel model, but again, we are probably normally going to get away with just Euclidean space because of we operate networks in the Euclidean space essentially. It could become more intricate if you start to put properties. So space is not the end of it. You could start to have many actions you could take, power, frequency, you know, and so on. So it becomes easily multidimensional. So it's not just the space itself. So if I start to say what channel I use, what power I use, what modulation scheme I use, you see, these are things that easily go beyond 3D, right? So, but let's say if you have a 3D space and one property, you can visualize things. For example, what we did, 2D channels, so you have a color map over 2D. But what I'm saying is if you start to complicate things, you add in time, and then of course you can't visualize everything, right? But essentially we are playing with some spatial abstractions. We are going to see what do they look like in terms of structure. We are not there yet, but one extension of the work we are doing could be actually seeing how time plays a role. And we had some initial discussion here in IIT KGP, how we could possibly do that. Because right now we essentially get a snapshot, and based on what we see, we compute our complexity and so on. But what happens if you start to have a dynamical evolution? Can you depict that? And this is not an easy problem in information theory sense. Normal information theory is about averaging things. You have the ergodic capacity, you have these things, right? But I don't know if there is really much work combining dynamical system studies and information theory. And after all, what we are doing are variants of information theory because we play with entropy essentially. So that's something could be interesting, but maybe not too easy. One thing we found out in practical terms is that if a communication system is more complex, it's also more robust to changes. So it's not just, you know, an intellectual exercise to write equations. We start to have evidence that it's actually a useful thing to be complex. After all, we shouldn't be surprised, because if it's useful for nature, it should be useful for us too as engineers. So visual representation of what I've been saying. So you could actually think of a network. Now this is a very regular lattice, but you know, we have to start somewhere. So every color is a different channel. So you have 3 pictures. So you have the left picture is like the usual way we do allocation nowadays. You actually allocate channels to neighboring cells in a very structured way, very regular way. Reuse patterns are like that, right? In cellular networks. On the right hand side, you have a random system where they basically every cell would pick a different channel randomly, and in the middle we have something which is based on self-organization. So you essentially, I'm making it simple, we are going back to that, but you observe what the neighbors do, and you act accordingly. So if you have a set of 6 channels, you are going to check how much the 6 channels are used by your neighbors. Why the neighbors? Because they are the ones with whom you interfere and that interfere you. So these are the ones you have to care about only. So if channel 1 is least used or maybe not used, it's a good choice. That's it, pretty much, okay? And that leads to something which even visually is something else. We kind of see that there is not much going on the right hand side, definitely a lot going on the left hand side. How about the middle one? Maybe something is going on. I don't think it kind of resembles something easy to classify even visually, okay? So what we found out is that, you know, if you actually use this self-organizing approach to things, we're going back to the complexity and entropy and so on, but the good thing is that it becomes more robust to changes. So if you start to change a channel allocation randomly for a certain base station, this would have some ripples, would have some cascade effects. If I start to interfere with you, then you might interfere with others. You kind of disrupt the thing, right? And if you use the centralized approach, it's actually more difficult to cope with this. Another thing we did, you kind of limit the changes to a certain area because you don't want an avalanche of effects. So you say, okay, I allow maybe the 2 outer tiers to do something. So I change my channel maybe at some point, and then I see what the system does. If I allow the system only to change in the 2 outer tiers, I'm not going to allow all the networks to change. That would be too much. So with this constraint, the centralized scheme normally doesn't do a very good job. It takes more changes to converge to something interference free, and sometimes you don't even have a solution at all. The self-organized scheme will always find a way through, and normally in a quicker fashion, okay? I have another, the last lecture I'm going more into details exactly about what we did with this self-organizing scheme. This is just some introduction. So the second bit of this degree of organization complexity, as we said, is the amount of information shared between parts of a system. An example of this is something that they used in neural, like in brain science. It's called neural complexity. And essentially it measures the degree to which a system has both some local and some global structures. So it's, again, this emergence connecting the 2 in between. So essentially how much you deviate from statistical independence at small or large scale. What I mean is, like, in a system that is not complex, the measure, if you want, of information would be proportional to the number of entities. If I have fewer entities, or if I have a larger amount of entities, I should see a line, because they all they are going to contribute equally to the system, okay? But in complex systems, you might have situations where, because of the interrelations, this is not true, and you might start to have deviations from this proportionality. I'm not going too much into the details because it would take a lot of time, but we started from this metric to do the work that we did in collaboration with IIT KGP. Okay, we adapted this to the study of wireless networks. In that case, we studied vehicular ad hoc networks, right? So, you know, I'm not saying we can necessarily tweak the system based on that, but we can study them. That we can do. So essentially, again, you have to have something in between local and global. You have to have some interaction at the local level, some effects at the global level, and it cannot be something like you just keep on adding things and you see that this metric of complexity goes up as a straight line. That's not what we are after. You have to have something non-trivial in the interaction between the parts, okay? So besides the theory, now we have the papers and so on, so you can go through them. It would take a bit of effort they're kind of a bit technical, but we do have a journal where we explain how we adapt actually this neural complexity to telecom networks. We have some concrete examples. We have a couple of papers one with IIT KGP about application. So there is a journal which I cite in the references, which gives you the bigger picture. I have to find the references. So is the first journal I list here in slide 1 to 2. That's where we describe the framework. Okay. So how do we apply this? So this basically, so there are two examples in this in the work we are doing. One is about the structure itself, okay, and one is how it looks like. That's what we, for that we used something called excess entropy, which I'm going to present in this course. And then there is another part of the work which has to do with exchange of information, which I'm not going to present in this course, okay, because of time constraints. But this second part, which I'm not going to cover, it could be useful because it's essentially something we could use to measure signaling complexity. Exchange of information, after all, is something we do daily in common networks. So, for example, to coordinate a network or to estimate the state of a network, we need to exchange signaling, and that's exactly what the brain does. The brain does exchange information to operate. So this complexity, they use it to study how the brain functions, and we are just mapping that to a communication network. It's networks anyway. Of course, we have to do some tweaks, but by and large, we use actually something that has been used in neuroscience. Okay, it's a very multidisciplinary field where we contaminate each other, and there are actually related fields, not necessarily using complexity, but for example, I have a project with these nano networks guys. So we use actually network tomography and machine learning for to try to understand the topologies in the brain. So you basically have a model like a simulator of the brain, so with different kind of neurons and so on, and you're given raw data essentially, and then from that, based on where the input is, so where the neuron fires, and you know the output of it, so you have basically a train of signals. Then you can see what topologies are there in the brain. So we found a lot of star topologies, for example. It seems in the literature that the larger you go with the scale, the more you start to see small world properties, which are something you encounter in graph theory. So yeah, it's not necessarily related to this, but what I'm saying is like you can actually, and a goal could be, for example, to study the capacity of neural communication, because some people claim that diseases of a neurodegenerative nature have to do with communication misfunctions. For example, Alzheimer, it's about a problem where you can't store things properly. It's a memory issue, caching if you want, okay? And other things like, I think, muscle dystrophy, this kind of illnesses, they have to do with some form of communication unreliability. So you basically, at some point, you have a kind of link broken in the communication sense. So they are trying to study these things with the lens of information and communication theory. So communication, telecommunication engineering and theory, it seems to me it's expanding way beyond its traditional boundaries. Okay, so and the tools of information theory and so on can be applied in many different fields. Okay, so this is interesting. For example, this example is interesting because it in a sense we are bringing home Shannon theory with what we do, because Shannon theory got applied into, for example, neuroscience, and then we are using some modifications they did to Shannon theory to use it again for communication networks, but the exchange is reciprocal. Okay, and that's interesting in my opinion, and I think it's a field that is coming up, this brain science and nano networks, and it could be actually possibly the future. You see, one thing I understand is like you need both the science, let's say the technical challenge, but you also need a market. Now the combination in nano networks is virtuous, because you have definitely very fundamental and challenging and good science you can do, and the market is human lives. So you are not doing it for the sake of people entertaining themselves with dull videos on the phone. You could literally change the way people live and age and recover from illnesses. So it's a very noble endeavor. So you see, and it makes money, because you know, if you actually come up with a solution to these problems, of course there is a huge market. Everybody wants to be healthy, or their relatives to be healthy, right? So we go back to this discussion we had before about the electromagnetic radiation. I think what the nanonetworks guys, I'm not saying they succeeded yet, they're working. What they're trying to do is cognizant of the fact they have to eventually get the business up and running, right? So the problem itself is well posed in that sense, because you're not coming up with a fake business model. There is clearly a business model there. If you do something like that, it would have an immense amount of financial profit, right? On top of solving actually, you know, noble problems from the human viewpoint. But you can't just go about things and saying, I'm going to do it because I'm nice. You see, you have to have a plan. And it seems to me these guys are doing the right moves in a sense. Okay, they have a plan. Yeah. More to come. I'm definitely I'm very ignorant in the field, but I acknowledge that, you know, sometimes academics, they are afraid to step into this because I'm going to lose the little bit of reputation I hardly gained. Which in my case is small anyway, so I won't have much to lose. But you see, the thing is, that's where it becomes interesting. You kind of go back to the day you joined the college and you knew nothing, but everything was fun, right? Everything was thrilling. So I think research gives you that chance, if you want to take it, to go back to basics and learn new things and become ignorant again, which might be a good thing, okay, to add more knowledge. And if you allow yourself to be, you know, in that uncomfortable position, you can actually do many new things and possibly expand the boundaries of your work and also the usefulness of your work. So you don't have really to change too much, but you have to accept you are at a loss in the beginning. You're not in your comfort zone, but that's where the fun starts, in my opinion. Okay, so if you do a bit of that now and then, might be healthy, and that's the way, for example, you could have a real impact on society. Not doing the writing transactions on 5G. You do that because that's how you make a living out of what you know. But especially for academics, you have the freedom to do other things if you want. So why not? Okay. So try to look into this, because there is a lot that could be done actually if people would join forces. It's still a minority, still a minor field. There is not so many people, but I know, for example, very good people in this field. So what I'm trying to do, I keep an eye on things. If I have a master student that is interested, I put it on this thing and we do some work together, and it could become something very, very interesting in the near future. So I hope if I give a course in 5 years to have work to tell you on that, because that would mean that the thing has worked out. But right now we are just in the pilot phase, so to speak. Okay. So maybe 6C is going to be about not about mobile phones in the end. Who knows? Maybe it's about the brain or something like that. Okay. So we take a break now, and then we have a Q&A session. About 10:30? Yes, please. Yes, 51, yeah. Okay, I'm not being very formal here, but essentially you have to write a program to describe the system, and then it's the length of that program. I don't know exactly how they count. Could be the lines of the program probably. So I think it could be the number of lines. Yeah, I've not been working with this metric specifically, but it could be one way. For example, if you have, say,
number of lines will be space complexity, and number of loops it's time complexity.
Okay. Yes. So you see, so it could do both, right? So what your colleague is saying is that if you count the loops, it's time, how much time it takes. But if you count the lines, it's space. Essentially, you have to store these lines somewhere, right? So the problem with this technique, though, is like it kind of overlaps randomness and complexity. And it could be okay. I mean, but to say something, the more random something is, the more complex it is, you're kind of missing the point that you have to use that in the end. So possibly, you have already metrics for randomness anyway. Entropy is about that. Okay, so I think you miss a bit the point if you use this metric for complexity. Another issue, as far as I know, Kolmogorov complexity. I'm not a computing guy, but they say it's uncomputable. So that leads to some problems again. I know people that are more in the computer science domain, and they didn't like this metric in the first place. So it was something we considered, because I knew that that was a possibility. But then my main collaborator in this, she's a computer engineer, she is an AI person, so she knows definitely more the CS world than me, and she said this is not a good choice because there are some issues with this metric, but people have been using it, so it's an option here. Okay. Any other question? Kolmogorov? Yes, this is what there is this field of, it's called algorithmic information theory. Possibly. I wrote a paper in 2010 where I just had a paragraph, and I said, I started to be interested in these things back then, and I said maybe I have a note, maybe algorithmic information theory could be the way to go. But then I didn't follow up on that because some people told me maybe there are complications, but it is a possibility, yes. I just didn't work with that, so I can't comment on the details, but it is an option. For information theory itself, they have their own, right, information theory. Yeah.
Integration, you are defining.
Yep.
Yeah. Integration basically defined by the difference that I have understood that whenever we are observing individual nodes.
Yes.
And the summation of the information we are getting from this, okay, and the thing whenever we are observing the total network as
Correct.
a whole.
Correct.
So basically we are if the integration value will be less, it will be good for us like that. If suppose I am observing any network and
Yeah.
The less integration value is desired, is it
The integration value is?
less integration
yeah.
value is desired because
I think, I mean, now there are integration is this I matrix. They are all kind of variants of entropy. Okay. So you see this expression is very small, but what they do essentially, you have neural complexity of a certain network. So they sum from 1 to n, this number of nodes, I think, and then they have the so this is what you actually measure. So this is the average integration for a network with I think up to k nodes. So you start with
we are dividing in suppose I have n number of nodes and I am dividing it two subgraphs. One subgraph consists k number of nodes.
Yes.
And another is n minus k.
Exactly. Yes.
So
It's the mutual information between these two sets.
yeah,
I think. Yes.
Interaction between these
Yeah.
subgraphs.
Yes.
How
Exactly.
they are working
Exactly.
in between.
So what you do basically, you see, you're right. So you take the mutual information between, say, k is 1. So you take the mutual information between individual nodes and the rest of the network. You average over all of them because you have different options for k equal 1, which are n options, right? You average all of them. That's this part of the story. Here you compute the total one, and you just scale proportionally. So what you're saying, I'm going to check the real thing, how it fares against proportionality, which is not what I want. So the more I'm far away from a line, the more complex I am.
Yes.
Correct?
Yes.
So when this guy is equal to this guy, you have 0, because that would be exactly what you don't want. You don't gain anything by interactions. You are just adding things. It's like the example of the teacups, kind of, right? Yes. There is actually, I think the paper is accessible. If you spend some time, I read it a couple of years back. It's very clear. So there is this Italian professor in US, Tononi,
Yeah.
and he was working. Yeah. So I think it's nicely explained.
And there
Yeah.
is another paper
Mm-hmm.
With a very good citation like 30,000 something.
Oh,
It
yeah,
is
yeah.
also
No,
very
Barabazi
yes,
is like one of the lead scientists in complex networks. Yeah. Yeah, no, I think they did apply, like Barabazi had very good papers about also about mobile networks, but especially about internet. A lot of citations. There are actually very good books, very good papers that go back maybe 20 years. They normally didn't apply though on what we do, like Phi and Mac for wireless, but there are some works that tackle information networks like internet and application layer of mobile phones, telephony. There is some work. Yeah, but these guys are basically simulating the brain, right? This computational biology. They use it for a very different context. Yeah. Okay. Any other question?
Sir, can you suggest any book on this field like application on wireless network?
Of
Good books.
of complex systems.
Complex system.
The first book will be the one we write. I don't think there are many. No, I can't suggest. I had a chat actually with Suvra, and we have a plan to write a book in the next couple of years. I can't think of a book. I will maybe chat with Miriam and the guys in Dublin. I wouldn't say so. I mean, there could be a good book of Barabazi about application to fixed networks because he did a lot of work for internet. Maybe that's not a bad reading. I suspect he might have a book. I'll have to check. But wireless, there is a team actually working on application of complex systems to smart grids in Finland. That's the closest I found because they also have quite a bit of telecom going on. But wireless, you know, Aritra, did you come across any such book? No? We have to write it down, definitely, yes. Okay, good. Anything else? Yes.
Sir, for example, I have a pen in this paper. Now, the pen is used to write on the paper, and the paper is used to record the writing.
Right.
So, can you tell me which one is more complex, in the pen?
Between the pen and the paper. Let me think. Okay, so well, this is more the support. So I don't know if well, you would have to see what you're writing. I think it's more like we are really talking about information. So the scale matters. So you might have the overall scale, then everything would be part of the picture. Or if you scale, if you start to zoom in, then you have the pen versus the paper. I wouldn't know pen probably, but it's difficult to say. I think one thing actually is interesting because you talk about the support. You do not have information in isolation. Information has to be recorded. So that's where physics come into play because you have to store things, okay?
Actually, the general question is, if you can't relate two things, for example, it's a pen and there's a bottle of water, can you find the complexity between the if they can't be related? They can't be related.
I don't know if you know what you could do. Well, it depends. First of all, what you would do with that. Okay, but you could if you have to have a model, a thing that tells you something about the structure. So you have to model this as a system. You have to have an abstraction where you have entities and the relations. Okay, and then possibly you could do that. So for example, in the glass of water, you might have the molecules of water. I'm not sure how easy it is to do that because they normally use statistical mechanics for these things. And the pen, you could have the components, and eventually once you build the graph, then you can start to compute things like this thing. Okay. Now, if I go back to this example. So I think they are probably, I'm not sure you can really compare them in the sense they probably belong to two different classes of complexity. So the pen might be something more, in my opinion, that is something like organized complexity because you have a moderate number of variables involved. A glass of water, when you're going to things like, you know, chemistry and so on, that's not so true. you probably need something like statistical analysis for that. That's what they normally do. You can't follow the individual water molecule. You can't do that, right? You don't have the tools, even the model for that. So what they do, they assume something about the specific molecule, let's say the typical molecule, how it interacts with others, and then they come up with some general properties. For example, they do it with gas. With gas, what they do, they say, okay, if a particle does this, when they clash, I have a model for the new directions, and essentially what happens is the faster you move, the higher you have the temperature and so on. But these are not things that you can, I don't think you can come up with a very neat equation. To do that, you need not a too large number of variables. But in general, two systems that they do not have a too large number of variables, you could model them as a system in the first place, as a graph, and then based on the graph, you can actually compute complex, and then you see, you just find out what it is. Now, I'm not sure this is too interesting though. So I think what is interesting is whether you can, let's say, for us as engineers, whether you can use it to model what we have. What does it mean for something to be more complex than another? Is it good? For example, what we found is if you are more complex in terms of communication systems, you might have benefits in terms of maybe you are more robust to changes. Or another thing we found with the guys here in Kharagpur, it might actually complexity be the proxy to trade-offs. For example, complexity might be related to some trade-offs of different nature. Some work we did is between scalability and energy efficiency. So it's more like if you could design your network to be that complex, you already know you get the trade-off you want without doing complicated optimizations, without doing complicated simulations. So it's more of a proxy. That's another option. I think that's fine. It's probably even more interesting, which is something we didn't do, if you can use this to write a proper design problem and solve it. For example, if you could somehow, right now we are just observing things, but if you could write sort of an optimization problem based on these things and show you do better than the traditional optimization, that would be very, very good. But we are not there yet. Right now it's more a scientific study, but you know we are trying to make it a bit more real and to use it, to design things. Now, one thing we are already doing though is, without using the more formal approach of information theory, complexity theory, is to use agent-based modeling. That you can do without equations, and to model your system and to make sure to show it works better than a centralized system. You don't have the equations, but you have simulations showing that. Okay, it's probably a bit less formal, and some people do not like it so much, but that we can already do. You can actually design your rules locally. You have some software system. You model your agents, how they interact, you run it. And then you compare with something that is done in a traditional way. We already saw some benefits of this approach, because especially when you have NP-hard problems, you can't really use centralized optimization for that in a useful way. So this agent-based modeling is good because you can always do that. The trick is to get the rules right, to model it right, but you see, it's not that you have to study 10 years of math. I mean, it's something, even with master students, normally we get something, okay? So the trick there is to publish in good journals, because some people have a problem with this less formal approach. I don't. I think as long as it works. You have to have a bit of both. I mean, a suggestion for those of you that are a bit more senior, that lead a group, be diverse. Do not put all the eggs in one basket. In my opinion, that's also a bit boring. So try to do, you can have actually, and you have to play the strength of your own research scholars. So if you have a PhD student, and the PhD student is a genius at math, do not put him to do simulations. The guy can do fantastic work in theory. But if you have, on the other hand, a guy that is very good at coding, or maybe is super good in experimentation, why do you torture the guy with information theory? So you see, you have to understand the strengths of the students and play with those. That's the better approach. You can't turn a square into a circle, right? But you can have a very good square or a very good circle. So that's my suggestion. So so in this field we have works that are more theoretical, that are more practical, and as long as they lead to some useful understanding, good. In fact, the theory is something we want to publish in journals, but the more practical approaches, we got good response from companies already, because that's what they want. So this ABM local algorithms is good because they say, okay, can I install it on my access point and get something out of it? Yes, good. They don't care about the neural complexity, right? So you have to see actually there are good avenues for good work of different kinds. You just have to find the right avenue. Some people have a template in mind. Okay, it has to be transactions. Therefore, I torture all my students to go toward that way. But I think you should just see what you have and get the right avenue. Experimentation is another great thing. So you can actually get tick in the box in different ways. So be creative. If you have actually questions also of a management kind, because something again some experience I'm accumulating, feel free to ask. You know, I can give you my views, how you manage a group, how you can make a group grow, how you can self-sustain the group with funds. These are not things necessarily related to neural complexity, right? It's more like experience, and they are as important, if not more important, for the health of a lab than the science. A lab is actually a company in the end. No profit, but you still need money to run it, right? So it's also very important that you get the management right. And people that are happy work more and better. Don't be obsessed by taking attendance sheets, in my opinion. Don't be obsessed by counting the days your employees are working. As long as they're doing great work, who cares? I mean, that's, again, my approach. Some people in Europe or in US would have a totally different approach. So be flexible. Okay, so we take a break and we start around, yes.